Hello, everyone. I'm Parecki, and I am very excited to be here and talk to you today about when things can go wrong with OAuth. I do want to add a quick note. They didn't actually ask me to put this in there, but I do want to make it very clear that this does not represent Okta's point of view on these things, and I will be calling out specific companies about some things that have gone wrong, and I don't mean to pick on them. They are just good examples of ways in which this stuff is hard. So it's hard for everybody. So a little background on me. I've been involved in OAuth for a long time. I maintain OAuth.net, which is the community website for OAuth. And I've also been involved in creating some of the specs that go into OAuth. And this is one of the recent ones we've been working on, recommendations for doing OAuth in browser-based apps because, again, this stuff is often hard to navigate and a challenge, so it helps to write these things down. I also recently wrote a book on OAuth, and we had a bunch of copies of this here at the developer booth, but they are, I think, all gone now, so apologies if you didn't get one. But yeah, this was published in conjunction with Okta, so this talks a lot about how OAuth works and things like that. So, I want to start out with a little bit of background about what OAuth is, why we have this at all, and what problems it's solving, and that'll help us frame this conversation about when OAuth does go wrong, we can kind of understand some of the context about it. So a long time ago, we had this pattern on the internet, which would happen over and over again. So every time a new app would launch, like in this case Yelp, it would ask you, hey, let's see if any of your friends are already using Yelp. And it would ask you to enter your email address, and then it would ask you for the password for your email address. Now, I hear some chuckles and like really, like is this for real? And yeah, like this was considered normal at the time, and like even Facebook was doing this. And like, can you imagine if Facebook did this now? Like this would just not fly. And like we understand now that this is a terrible pattern, but there wasn't an alternative in 10 years ago. So what's actually what the goal here is that this app, like Facebook or Yelp, it's trying to get access to your address book so that it can compare the list of your friends with people who have already signed up for this service. It's trying to get access to this one API, the Google Contacts API, and it doesn't need access to your email, and they don't actually want access to your email. It's just that the only way to do that was to have them both together. So there's obviously several different ways this could be solved, and one of the but also many ways in which tried to solve and it didn't work. And the Yelp can't just go and ask Google for random person's address book, and the app shouldn't be allowed to ask the user to enter their password and give the password over to Google. So what the problem statement here is, how can users let this app access some part of their account without giving it their password? Because people did want that, the end result of Yelp has access to your address book so that it can see who else is on the network, and you have all the friend connections already there. And people wanted that so bad that they were willing to give their password to this thing they're asking for, because that was the only way to do it. So this is the problem being solved by OAuth, and now instead of a type in your password field on these apps, now it's connect with Google. So this is now a much better pattern, and now instead of typing in your password into your Gmail password into Yelp, you can go and log in to Google. Google gives you back a thing that you can take over to Yelp and give Yelp this sort of temporary access to one particular part of the account instead of having to give it your entire account credentials. The thing that ends up getting used in this case is called an OAuth access token, and the access token is basically just a string that represents that a user has allowed an application to access their account. That string is used in API requests like this. So you can think of that like a key. It's a key that can do just one thing. It's kind of like a hotel key card. So when you go to a hotel, you check into the front desk. You log into the front desk. You show them your ID. And they give you back a hotel key card. That's like an OAuth access token. You take that key card, you go to the hotel door, you swipe at the door, and the door opens. Now, the door doesn't care who you are. The door has no desire, no need to know your identity or a unique ID or your name or anything. All the door cares about is that whether this card can access this door at this time. So that's the same thing that happens in OAuth, where an OAuth access token doesn't necessarily have to represent a user, although in many cases it does. But it represents access to data. Okay, so we're going to talk a little bit about how OAuth works and how some of the data moves around in this world, which will help set us up for understanding some of the problems. There's typically these 4 roles in OAuth. There's going to be the user who has an account at some server and some data that lives over in the API. There's going to be some application that they're trying to use, like Yelp, or a web app, or a mobile app, or whatever kind of application that is, and that's called the client in OAuth terms. And then the OAuth server is the thing that's responsible the OAuth server is the thing responsible for creating access tokens and asking the user if it's okay for this application to get an access token. Then, of course, once the app has an access token, it can go make API requests, and then the API has to know how to check access tokens. And so there's a lot of data flying around back and forth, right? So let's walk through a typical OAuth flow and exchange to see how this data moves around. Start out at the top. The user is sitting in front of their computer or using a mobile app, and they are going to go and look at this application and say, hey, I would like to use this. And it's going to be clicking a button that says, like, log in with Google. The application will say, cool, okay, go over here so I can get access. Then the user's browser will go over to the OAuth server and say, hey, I would like to use this application. It wants to access my photos or my contacts or whatever that is. That will then cause, assuming the user clicks OK, the OAuth server will create a temporary code, give it back to the user. And the user then takes it to the application. And the application is like, great, here and now I can go get a token with this. So the app says then to the OAuth server, here's the temporary code I got from the user. I would like an access token. And the server replies back with an access token, and now it can go make API requests. So the interesting thing here is that the way this data moves around is very different between the first part and the second part. And I colored these lines down here pink to demonstrate to call them out here. The lines at the bottom are what we call sent over a back channel. And the back channel is the idea of sending data from one thing to a server over a secure connection where the response comes back immediately. It's like your typical HTTP request or REST call, right? We're very used to that kind of way of sending data. The idea of sending data over the front channel is probably less familiar. And the point there is that we actually, because these two things don't necessarily have a way to communicate over a back channel, we'll actually send that data using the user's address bar. And because it's using user's address bar, there's many ways that can go wrong, many ways it can fail. The user can modify the data. Some other software on the machine can modify data. So obviously there's a bunch of benefits to sending data over the back channel, right? The thing making the request knows what server it's talking to because it checked the SSL cert. That connection is secure, it can't be tampered with, and then the response that comes back is part of the same connection, so the thing getting data can already know it's trusted. So it's like very carefully handing, by hand, data from one to another. Whereas passing data over the front channel is like throwing it in the air and hope they catch it. So why do we use the front channel? It turns out there are some benefits still, and one of the benefits is that it forces the user to be involved in the process so that you can ensure that the user did in fact give permission for this to happen. And secondly, it means that the thing receiving data doesn't need to have an IP address on the internet. It just needs to be some code running on a device. So that lets it work on a phone or lets it work in a browser-based app where there is no public IP address for that application. This does, of course, come with a bunch of risks. So from the sender's point of view, the sender is going to be sending data through the address bar and has no guarantee that it's going to make it to the recipient. Because it's written in the address bar, it becomes part of the browser history, which means it may be synced to the cloud. So if you're signed into Google Chrome, then your browser history is synced up to Google, and then probably synced back down to your other browsers. And then from the receiver's point of view, if you receive data over the front channel, you can't actually guarantee it came from the right spot, because somebody else could have thrown you that data, right? Okay, so here, this is kind of the setup. We have the flow of all these different parties. Some of the data gets sent over the front channel, some gets sent over the back channel. Who's trusting who? So let's talk about some of the ways that things can go wrong in OAuth. It actually turns out there's a lot of different moving parts here, and a lot of things can potentially go wrong, and there's a lot of things to protect against. So, there's a lot of API keys involved here, so you have to make sure those don't get stolen. When there's access tokens issued at the end, and applications have to make sure the access token can't get stolen. While sending the data over that front channel, there's that redirect that happens, which means you need to make sure that can't be intercepted or intentionally, redirected. Then there's still phishing. OAuth is not immune to phishing attacks. They just look a little bit different in the OAuth world. There are so many tricks in this space and so many things to be aware of that there are actually multiple documents dedicated to documenting them. So it's starting with the RFC 6749, which is the OAuth core spec. There's a section in there that talks about several common threats and ways to avoid them. And that was written quite a while ago now, and those are sort of the well-known ones. And then a few years later, there was this 8252, which talks about some new problems related to tokens and things like that. And then there's 6819, which is like a document dedicated to just security topics around OAuth. And there's even a new one, which is in draft right now, which is a whole host of new things, since OAuth has kind of evolved a lot in the last 10 years. So there's a lot there to read, and we try to make this stuff easy to read, but there's really a lot there. So let's talk about the first example here, and that is from Twitter. So in 2013, we saw a bunch of headlines like this. Twitter's OAuth API keys were leaked. The secret OAuth app keys to Twitter's VIP lounge. I don't know, that's just a very sensationalist headline, but fine. What actually happened here? Twitter is obviously has like an iPhone app, an Android app, a Windows app, back when Windows was a thing. And the way Twitter's OAuth API works is it requires signing every request with a secret. So you need a secret for the app, and so Twitter goes and makes a secret for their iPhone app, makes a secret for their Android app, puts it into the app, ships it to users, and everything works fine, right? Well, turns out that when you try to put secrets into mobile apps, they're not secret anymore, because it is trivial to decompile the app and see what's inside or watch network traffic. And anything that's secret in that app will just not be a secret. So someone was like, oh, cool. Let's go and collect all of the Twitter API keys and put them on GitHub and see what happens. So this was the leak of, all of Twitter's secret API keys were leaked. And yeah, because they're not secret, and that should never have happened. So what's the end result of this? Well, it basically means that anybody can impersonate the Twitter app. So that's going to be like, maybe not the end of the world, maybe it's not, like you're not going to get access to somebody's data, but a developer can create an application that will appear to users as if it were the real Twitter app when it goes through the OAuth process. And probably more importantly, this was also around the time that Twitter was starting to lock down their API and impose like rate limits for new applications, which really meant that the end result was a developer could go and use the Twitter API for their own accounts without any rate limits, because they could pretend to be the Twitter app instead of having their own developer credentials that had more strict rate limits. Okay, so what's the moral of the story here? Don't put secrets in native apps, because you can't. They're not secret. I wrote a blog post a couple months ago about this, and a link is down there. or just Google API keys aren't safe in mobile apps, and you'll find it. And that talks basically about, it goes through a couple of ways that you can very easily see how it is not safe to put secrets in mobile apps in case you need to cite this for some coworkers who maybe don't understand it yet. So how do we solve this in OAuth? Well, it turns out this is actually one of the reasons that OAuth 1 was scrapped and replaced by OAuth 2. Twitter still uses OAuth 1. They haven't migrated yet. So in OAuth 2, we have a solution to this, which is we don't use client secrets for mobile apps. Instead, we use pixie. So PKC is pronounced pixie. It stands for proof key for code exchange. It is an extension to OAuth, and basically what it does is it takes the place of the need for a client secret in the OAuth exchange. So given the authorization code flow that we saw at the beginning, all of that still applies. We just do something before it starts and right at the end. So let's walk through that really quickly. Here's the flow diagram we saw before. It starts out the same. The user says, cool, I would like to use this application. And before the app sends the user to the authorization server, it says, okay, cool, hang on. I'm going to go make up a new secret right now. So it generates a new secret every time. And then, importantly, it hashes it. And the trick with the hash is that a hash is a one-way operation. So if you think of just think of 10 random numbers and write them down, add them all together, and then give that number to somebody. They won't be able to tell you what 10 numbers you wrote down, right? Because it could be several different versions of 10 numbers. So it's like that, but cryptographically secure. That's not a good hashing function. Don't use it in production. But the point is, this app will generate a secret and then hash it, and then the hash is what is sent in the URL. So the hash is the thing sent publicly in the browser. The user can see it, but it's fine because nothing can reverse engineer it. Then the user goes over to the OAuth server and says, hey, I'm trying to log into this app, and here's the hashed secret it gave me. And then the OAuth server replies back, cool, here's the temporary code. That's the same as before. Nothing changed with that step. The device then goes back to the app and says, hey, here's the temporary code. Please use this to get a token. And now here's where it's different again. This time, when the app gets the code, it doesn't have a secret, so anybody who steals the code could normally exchange that for an access token, but because we're doing pixie, the app has to also include the plain text secret that it used to generate the hash. And remember, this is the first time the secret is sent anywhere, so it didn't have a chance to get intercepted ever because it hasn't ever been sent. And this is being sent over a secure channel, so there's, again, no way to intercept it. The server then says, cool, let me hash that secret and check if it matches the one I saw at the beginning. And if it matches, it knows that that code wasn't stolen. And now everything continues as normal. So thankfully, you don't have to remember this usually because it's all handled by the library that you're using. So if you're using the Okta SDK does this for you. If you're using a server that doesn't have a library of their own, OAuth is a good library to use as well. And this will handle that hashing stuff for you. OK, so next example. Stolen access tokens from Facebook. This was a recent one. This was in 2018. And you probably remember these headlines, right? It was like 50 million Facebook accounts were exposed or hacked or however they were calling it. And because this is Facebook and because this was 2018, there was a lot of eyeballs on Facebook and everybody was wondering how this happened. And Facebook decided to actually publish a surprising amount of detail about the hack. So we can actually go and look at what happened in detail and try to understand what was going on. I personally don't think these kinds of headlines are very useful, but if you go and actually look under the hood and find out what actually happened, we can learn something from it. So it's going to take a couple of steps to build up to this, so bear with me here. The problem that happened with Facebook was actually 3 different bugs stacked together. And each one by themselves weren't that bad and maybe weren't a deal breaker. It wouldn't have led to 50 million account compromise. But when combined, this is what happened. So first bug. So when you go to somebody, when you go to your own Facebook profile, you can see what your profile looks like as to other people, which is actually a very cool feature. And it's good on Facebook for doing that because that's a pretty cool thing that helps people understand better about their own privacy controls that Facebook's giving them, right? So great feature, but if you were on your profile, you could go and say like view as your friend or your mom or whatever, and then that was supposed to be a read-only view of your profile. There was a bug where it incorrectly put a little box that would let you post a video to your timeline. Because like when you go to someone's page, you can like post a video to their timeline on their birthday. And there was a bug where this view as feature then showed that box. Okay, this doesn't sound that bad, right? Like no big deal. It just like incorrectly showed a input field. So hold that one in your mind for a little bit. Second bug, unrelated. They made a new version of the video uploader, which was the thing that would pop up. And that incorrectly generated an access token that had the permissions of the Facebook mobile app. Normally, this video uploader is supposed to have the permission to just upload a video, right? So you can imagine like whatever you're doing with your access tokens to control the capabilities of that access token, it was supposed to be limited to the ability to post videos. Instead, it had permissions of the Facebook mobile app, which means basically it can do anything, because the mobile app can do almost everything. Okay, so hold that one in your mind now. Third, when the video uploader appeared, uh-oh is right. It generated the access token not for you as the viewer, but for the user that you were looking up. So again, by itself, this wouldn't necessarily be a huge deal, because it was supposed to have generated an access token that could only upload videos. But because of that other bug, it then had the permissions of the Facebook mobile app. So you stack all these three things together, and you end up with this. You could go to someone's profile, you can go to your profile, use the view as feature to see what your profile looks like to somebody else. You would end up with an access token that belongs to that user, which has the permissions of the Facebook mobile app, which is just like, holy crap. And that essentially is a complete account takeover, and you can do then anything that that user can do. Yeah, that is how that spread. So how do you fix this? Well, this is tricky, because like there were three different things that interacted in ways that nobody expected that stacked up to cause this bug. But I think the core of the problem is that essentially Facebook was allowing their own internal components to impersonate other internal components in ways that were not appropriate. So treating your own components of your applications the same way you would treat third-party applications, I think would help avoid this kind of situation. Because if you imagine like somebody had to write code that would let this part of their internal app then swap out and pretend to be this other part of their app. And like that just shouldn't have ever been written. That kind of code shouldn't exist in your application. And if you're using OAuth and OpenConnect properly and making sure every component is treated separately, you won't get into that situation. And if you are treating all of your internal development teams as third parties, it's even easier to sort of keep that from happening, because everybody ends up being very separate and isolated, and you don't share data and mix it inappropriately. All right, so example number 3. JSON Web Tokens, JWT, or also pronounced JOT. There was a problem with many, many libraries for JSON Web Tokens, and this sort of all blew up in 2015. So JSON Web Tokens, let's back up a little bit. What is a JSON Web Token? It is an encoding mechanism for signed data, transmitting data from one to another in a signed way. But it is also often used as a way to encode access tokens. And it is used as the OpenConnect ID token. This is what a JOT looks like. It looks like nonsense, but it's not. It's also not encrypted. It's just base64 encoded JSON data. So if you look carefully, you'll find 2 little dots in there. And if you split on the dots, it turns into 3 parts. And the 3 parts are a header and a payload and the signature. So the header contains information The header contains information about the token. The middle part, the payload, contains the data you actually care about, like user ID, the groups they're in, the expiration dates, scopes of, if it's an access token, it'll include like scope information. And then the bottom is the signature. So the way JOTs work is the thing that creates one has some sort of secret, usually a public-private key pair. It will create the payload that it wants. It'll say, all right, I'm going to sign this with this signature algorithm, and then use its private key to create a signature, put that at the bottom, and then this all gets base64 encoded. Then when somebody wants to validate the JOT, it will read the JOT and be able to know that if it was signed with a signature method, it goes and finds the keys, the public key, checks the signature. That's all great. The problem with the libraries were that they were using the header algorithm here to determine how to validate the token. So if you think through this for a minute, you look at this in your code and you're like, okay, is this valid? So far, it's external input, so you can't trust it initially, so you have to validate it, obviously. The problem is that they were, if you look at the algorithm to check how to validate it, you're using unvalidated data to check if it's valid. So the attack here is that the attacker could just change the algorithm and tell the library to validate it a different way. The subtle attack on this was that if you change RS-256, which is an asymmetric signing algorithm, to HS-256, that is a symmetric signing algorithm, then an attacker could actually use the public key component as a shared secret, modify data, create a signature, put it back and make a new JOT and give it to somebody, and the library would think it's okay. The more blatant problem here was whether there is also a signing algorithm called none, which means there is no signature. I don't know why this was a good idea at all, but the attacker in this case could just make up whatever stuff they wanted in the payload, change the algorithm to none, give it to some server. The server would be like, cool, how am I going to check if this access token is valid? Well, signing algorithm is none, and I don't see a signature, so yeah, checks out. Yeah. So I guess the moral of the story is don't let the header determine the way you're going to verify the JOT, because that is unverified, untrusted input. And just same way that you don't trust external input in like regular web apps, and you have to like validate all external input. This is the same thing. This is external input until you validated it. So thankfully, I'm pretty sure all of the JOT libraries fixed this in 2015, 2016. They all published updates, and the fix is that when you're validating a JOT, you now in your code have to tell the library which algorithms you accept. So you can still shoot yourself in the foot if you say that you allow the none algorithm, but if you just only ever have one signing algorithm, you just put that in the thing, and then now you're fine. So, all right, last one. This is a really subtle one, and this was a problem with Google's OAuth API. So this went around in 2017, and this was called a phishing attack or OAuth worm, or had a couple of different names in the press. But here's what happened. First of all, anybody see anything wrong with this picture? This is a real browser. We're really on accounts.google.com. There's a real SSL cert. So, we're not looking at a fake website. Looks pretty normal. What if you click the little Google Docs and this pops down? You see anything wrong now? What is docscloud.info, right? That looks a little bit fishy. So what's going on here? In this case, the attacker went to the Google developer website, registered for an account, went in and made a new OAuth application and called it Google Docs. Uploaded the icon for Google Docs into that application. That Google happily was like, cool, here's a new app, here's a client ID and client secret, and issued credentials to that application. So it is a real OAuth app. It has its own client ID and client secret. Then the attacker can take that client ID and use it to create an OAuth request URL. And that's going to be like we saw at the beginning, where the app wants the user to sign in, so it makes that request URL, puts its client ID in that. And then when you visit that, you'll see a prompt like this, which is Google Docs would like to read and send and delete and manage your email and manage your contacts. So these are scopes that this app is requesting in OAuth terminology. What do these scopes let this app do? Well, as soon as one person clicks this, then Google will issue an access token with these scopes. So there's no hack here, right? This isn't really a hack yet. Then that access token can be used to go and download the person's address book and then use the Gmail API to send email from their Gmail account to their friends. What are they going to put in that email? So-and-so shared a file with you. Click here to view it in Google Docs. Now when that person clicks the link, opening Google Docs, they're expecting to see a Google Docs window, so they just click OK, and then the process repeats. And this is why it's sort of like a phishing thing, right? This isn't even a spam email. This is, the one on the bottom is not spam. It's sent by Google to another Gmail account from an OAuth, thanks to an OAuth access token. So as soon as one person clicks that, sends the email, then the next person is ready to click OK on this screen because they're expecting to see a Google Doc. And then it just spreads and spreads and spreads and spreads. And it happened so fast, within 40 minutes of it starting, Google tweeted this out. And they were like, we're investigating this phishing email. It appears to be Google Docs. We don't click anything right now. And there was also a Reddit thread where this got posted. And in that thread, I need to find it again because it was amazing to watch this unfold in real time. You could see Google engineers chiming in on the thread, being like, oh, we're looking at this. Oh, this is kind of strange. Oh, what's going on here? And they were like, you could see the thought process of all the engineers at Google unfold in that thread. And finally, their fix was to just disable the client ID, because as soon as the next person clicked that link, then they would see this error. And that effectively stopped it from spreading. It's also, there was no real attack on the protocol on OAuth here, so it was also very easy to just shut down all the access tokens because they were all associated with that one application. So just, blacklist the app and everything's fine. But that doesn't really solve the problem, because the problem wasn't that someone got an access token. The problem was that users were tricked into allowing this application. And it turns out that is a very, very, very hard problem to solve, because it is trying to teach users things. And anytime you have people in the mix, things are just going to be less secure, right? So the real challenge here was that the prompt for permission did not provide enough context to the user to know that something was wrong. And that is the idea of user consent. So the challenge is designing this consent screen in a way that people can actually understand. You want to inform them what's going on very clearly, but you don't want to give them so much information that they just click yes because they didn't read it. So here's Google's, and this is overall pretty well done, pretty good considering the complexity of Google's API. They have hundreds of APIs and very complicated scopes within those APIs, and they do a pretty good job of showing it. But as in this screenshot, how do I know this is the real Slack asking for permission? Anybody could make an app called Slack. So that's the problem. They haven't actually fixed that yet. But they do a pretty good job of showing the scopes and with progressive disclosure of if you want more information about what this one means, you can get it. So let's look at some other examples of other APIs. This is the Wunderlist OAuth consent screen. And I like that they have this on the left, this app can do these things and it can't do these things, on the right in red. But I don't think it's actually very well branded. If this suddenly appeared because I clicked something, I wouldn't actually know I was on the Wunderlist website. It's not branded well. Here's Flickr. Flickr is one of the older OAuth APIs. They were part of building the spec. And they again do that here's what the app can do, here's what it can't do. They explicitly call out deleting photos as a permission that apps have to request and show the user that this app won't be able to delete photos. So those are all good things. I think this is also, this is kind of a dated look for websites now, but it is functional. Here's Spotify. I don't even know what to look at first on this screen. Like, the permissions it's requesting are actually written in 2 different font sizes. And I don't know why there's like a privacy policy blurb in the middle there. So pretty much if anybody sees this, they're just going to click the green button to make it go away. Here's GitHub. GitHub is another one that has a pretty complicated API. There's a lot of permissions involved in the GitHub API. And they do actually a pretty good job of explaining it. They show the scopes, they show the user account that's logged in, they show the scopes, they show which organizations are about to be, have their organization data authorized to be used by the application. And down at the bottom, they actually show you what website the application is running on so that you know where you're going to be sent back to. And that is, I think, a really important part of indicating whether an app is legit or not. Facebook is an interesting one. Again, Facebook is a very complicated API with a lot of moving parts. And this is a very clear and straightforward screen. And the really cool part here is that if you click Edit the info you provide, you can actually decide that an application should not get certain access that it requested. And this mechanism has been built into OAuth from the very beginning. There's nothing in OAuth says that just because an application requests some scopes that the server has to allow it. Like, the server is welcome to just issue different scopes at the end of the OAuth flow. And Facebook is one of the few that actually took advantage of that part of the spec. Fitbit did as well in a very literal sense. So they have checkboxes where you can just uncheck scopes. So I think that's pretty cool as well. So if we look at all these together and kind of try to find what are the commonalities between all of these that make a good consent screen, I think it boils down to this sort of prototype where you want to make sure that you're clearly identifying where the user is, what service is this. Make sure that you identify the third-party application, both by name but also by URL, and also probably show the developer name. Show which user is logged in case users have multiple accounts. And showing the scopes that the app is requesting. And then, of course, there's always the allow and cancel buttons. So hopefully this has been useful and you've learned a little bit of what can go wrong and how to fix it. There's a lot more information about this at OAuth.net/security, links out to those RFCs I was talking about with a lot more reading you can do. OAuth2simplified.com is the book, and I hope you grabbed a copy if you were down at the Developer Lounge already. And yeah, this is me. Follow me on Twitter. My website's aaronpk.com, and I will be down at the Developer Lounge for the rest of the day. So thanks. We have about 5 minutes for questions, so we can take a couple. Should be a microphone, so if anybody has a question. Also, before you leave, please do rate this session in the mobile app. And I will leave this screen up while we do questions for a couple more relevant sessions today.
I have a question. So for Okta 2, we have API tokens. And there isn't a capability where we could limit on what APIs that the API tokens can be used for. Is there a plan to build it or bake it into Okta in the near time?
Caveat this with, I am not fully informed about the roadmap of Okta. I believe there is, and I don't know the details. Come down to the Developer Lounge because I will be able to point you to someone who actually knows the roadmap.
Okay, thank you.
Hey, so with stolen API keys and using Pixie, that didn't seem to solve the problem to me in that the problem was really you don't know if a native app is truly the real Twitter app. So just by hashing a secret I generate doesn't prove that to me, right?
Yes, so that is a very subtle point, and you are absolutely correct. Pixie solves the stolen auth code problem. It doesn't solve the client authentication problem. And there are a couple of things you can do in terms of just stronger validation of redirect URLs and using the app claimed URLs instead of custom schemes that sort of help get closer to stricter authentication for the client. But ultimately, true client authentication is almost impossible to solve. Luckily, that's also less of a problem than the problem of getting authorization code stolen during the flow. And Pixie does completely solve that part, which is a bigger attack surface, and is thankfully then solved very cleanly by Pixie.
Gotcha. Thanks.
You didn't mention app attestation, and I've seen that a few times in the OAuth specs. Can you describe the threat that app attestation is intended to mitigate?
No, but come ask me later. Thanks. There's a lot of experimental work that I would consider not quite like in production, ready for production yet, and I think that kind of is closer to that side of things, but we can talk about it later.
Hello. For the JWT algorithm header issue, couldn't have the issue been solved by including the header in the signature, like while creating the signature? Because if you tamper with the value,
I didn't quite understand that. Including the header in what?
Like when you're creating a signature, instead of not just including the claims, if you include the header as well, right? Then if you tamper with the header, then the signature would change, right?
Right, but the problem is you don't know. You need to know. You need to take a chunk of data to sign, to check, and that data that you take is untrusted until you check it. So even if the header was part of the signature, anybody could modify the header and modify the signature to make a new jot, which would validate.
But then you don't have the private key to create the signature, right?
Right. So there's no way to spoof it with a private key. The problem is that the problem here was that you could change the algorithm to tell to validate it differently.
Okay.
I think there's one more question. Nope, great. Okay, thank you all for coming. Thanks so much. Don't forget to rate this in the app. Thanks.